Today, I will give you a brief presentation concerning task 5.1 within work package 5 of Impress. And as you can see from the title of my presentation, this task is related to innovative workflows for the design and development of multipurpose MEMS devices for operando application in battery research. Before I start, I want just to give a brief outline of the presentation. So after a brief introduction where I will generally address the topic of battery research and in situ transmission electron microscopy, I will talk about task 5.1 and how it is organized. You can already see that is divided into subtasks, task 5.1.1 and task 5.1.2. And for each task, I will give a general overview of what have been done so far. And at the end, I will present you a workflow and telling you what are the next step of the task. So battery research is indeed the quest of the new era. I here reported a graph that I find this nice review. And this graph displays how in the last 15 years, the interest in battery research has grown and grown. And the reason why there are so few publications in 2023 is because this review has been written in early 2023. So indeed, the reason behind this huge interest in batteries is because they have a strong impact on society and everyday life. Here I reported just 3 examples, but I could have reported many more. Nowadays, car selling companies are pushing towards the substitution, let's say, of the conventional car with electric cars that totally rely on batteries. And all of us have portable devices, and all of us want that the batteries on those devices can last longer, can be lighter, and can possibly be cheaper. And then all the processes related to the production of energy, exploiting natural resources or renewable resources are aiming indeed to produce energy, but once that energy has been produced, it must be stored somewhere. And once again, we need battery to store that energy. So the main two goals of, let's say, two of the main goals of battery research are related to the improvement of the performances of the current generation batteries, as well as the engineering of novel, more efficient, and more reliable type of batteries. And in order to pursue this goal, we need to understand the properties of the composing elements of the batteries, so electrodes, by studying the structure and the chemical composition of them. There are 2 powerful techniques that allow us to do so. And one is indeed in situ TM, which can allow us to gather local information, so of the atomic structure of the components of batteries, so we can indeed gather information and understand the properties at atomic scale. Whereas in situ experiments at synchrotron facilities can allow us to gather insights on the composition of electrodes and their alteration in working conditions. So we can gather information and indeed understand property of the bulk materials. And if we combine these 2 types of information by means of correlative studies, we can indeed pursue the 2 goals that I mentioned you in this previous slide. And this is indeed the idea at the basis of task 5.1. So we want to indeed engineer, or at least try to implement an interoperable cartridge-based systems for electrochemical experiments at operando conditions. And those experiments will be run both inside transmission electron microscopes and a synchrotron facility. So as I told you at the beginning, task 5.1 is divided into 2 subtasks. The first one is related to the development of a new concept of miniaturized microfluidic electrochemical device to study liquid batteries at operando conditions, whereas the second is focused on the development of an innovative cartridge-based electrochemical microreactor to study solid-state batteries at operando conditions. For what concerns the first device, here I listed the characteristics that we we thought. On the right-hand side of the slide, you have a simple sketch that represents the cells within the device. This cell is basically composed of two chips, a bottom chip that hosts all the major components and all the relevant parts for the in situ experiment, a top chip, and in between these two chips, there is an O-ring that prevents liquid electrolytes from leaking outside the cell. So this is a microfluidic closed cell configuration where battery electrode can be directly deposited or grown on working electrodes or counter electrodes of the cell. These devices allows us to dynamically inject liquid electrolytes inside the cell without exposing it to air during the whole experiment. And indeed, this device can allow us to have a direct relation of the electrochemical process that occur within the cell, inside the cell, during the experiment, with the observation that we can indeed achieve by means of electron microscopes. This is the design of the bottom chip of the cell. And as I told you in the previous slide, it hosts all the important components for the in situ experiments. We have two working electrodes and two counter electrodes. There is a heating element because during the experiments, we also want to study the behavior of the batteries at different operating temperatures. There are a few spacers in order to help with the alignment of one chip with respect to the other, but also to guarantee a minimum amount of volume within the cell. There are two imaging windows, a reference electrode, where lithium can be deposited and it can be used as a reference electrode for standard liquid ion batteries. There are an inlet and an outlet that allows indeed for the liquid electrolytes to flow through the cell. And finally, there are two piezo actuators that will allow us to indeed modulate the thickness of the electrolytes within the cell, because once those piezos are actuated, one chip will move far apart with respect to the other, and in this way, we will be able to indeed tune the volume within the cell, and in this way, indeed modulate the thickness of the electrolyte. This is the design of the top chip. Is quite simple compared to the other chip, because it only hosts the O-ring. So it has a groove for the O-ring and two imaging windows that are, of course, mirrored with respect to the bottom chip. And these windows are, of course, for actually make the electron pass through the cell. For what concerns the second device, here again, I reported the characteristics of the cell together with a simple sketch of it. So we chosen an in-gas closed cell configuration that will allow us to have a certain control over the environment, the working environment of the solid-state batteries. And the reason why we want to control the environment is because this can allow us to study also the most sensible type of electrodes. In this case, the solid-state battery lamella will be prepared by means of focus ion beam and will be deposited on the bigger chip. We also want to implement a reference electrode that can be moved in 3 dimensions, so in X, Y plane, and also in Z, in order to locally reach precisely reach specific sites of the lamella and study local properties, as for example conducibility. And then we will also want to work at variable pressure of gas and also variable temperature, once again making use of an heating element on the chip. This is the design of the small chip. It actually hosts the reference electrode. It has 4 spacers that prevents the 2 chips to directly touch. Then there is an imaging window and 2 feedback sensor for the position in order to monitor the position of one chip with respect to the other. But the main feature of this chip is indeed the presence of a tip on the reference electrode at the very end of the reference electrode. And this tip will allow us to indeed study the local property of the lamella. But this tip can be also heated or it can also use to deposit lithium locally, because if lithium is scratched, a lithium reservoir is, let's say that the lithium present in a lithium reservoir of the cell is scratched with this tip, the lithium present on the tip can then be deposited on precise site of the lamella. This is the design of the bigger chip, let's say, and it's quite simple. Once again, we have two working electrodes and two counter electrodes, an imaging window, the feedback sensor for the position that are mirrored with respect to the other chip, and an heating element whose design still is must be still finalized, but we are actually finalizing it in these very last days. So with this, I came to the conclusion of my presentation, and before greeting you, I just want to show you this workflow that presents you all the steps of the task. So at the moment, we are at this step because the object of the study and the methodologies have been conceptualized. The design of the chips have been drawn, and most of the elements have been finalized, except for a few ones. Now we are planning to produce basic prototypes of the chips without many elements, let's say just basic elements that allows us to perform some preliminary tests. And we will also produce some cartridge-like prototypes in order to run those tests. And those tests will mainly devoted to understand if those designs are adequate to withstand vacuum, and if there are no leakage of liquid or gas. And also we'll perform some tests by means using indeed piezo actuators in order to understand if all the movements are possible to perform. Then, if those tests will provide us with satisfying outcomes, we will move to the production of the complete chips, the final chips, with which we will perform all the tests, the previous tests, but also the final experiments within the microscopes. With this, I finish, and I thank you for your kind attention.